All right, Mr. G Math coming at you live again, 7202. Lesson 6-3. Remember we talked about trapezoid, and I said you can't avoid what the formula for a trapezoid is because we're going to use it. So if you were paying attention in 6-2, you could notice that rectangles are not the most efficient shape to use to really approximate the area under the curve. There are times when those rectangles do not approximate very accurately, that they don't really cover the space. But what shape can cover the space better for a more accurate answer? And yes, the answer is trapezoid. So let's see why a trapezoid is a better shape. So the area formula for a trapezoid we know is 1/2 the basis times the height. And we're used to trapezoids perhaps being sideways where you have the base on the bottom and the top. But if we rotate that trapezoid, that's what it's going to look like, how it's orientated. So the bases are really on the left and the right rather than the bottom and the top. And the height is actually at the base where the bottom would be. Now, when we think of a trapezoid in terms of what's happening, we can't have to rearrange our thought of what base, height, and width means. We know that these here are actually your bases. But I also can think of it, there are certain heights, right, to the graph. So this height and this height really together make your bases. And this width is really the height of the trapezoid. But we're going to change how we think and talk about these heights and then the width. When we say width, we mean the height of the trapezoid. These heights are actually the bases of the trapezoid because we've reorientated them. All right. Since trapezoids used in the approximation of areas are usually positioned vertically, we will write this formula. So instead of the height, it's the width, and then the bases become the two heights to reorientate how we see them. That will take a little bit of time, but once you're used to it, you're going to be comfortable with it. To approximate the value of a definite integral using trapezoids, use the same strategies as Riemann sums, but add the areas of trapezoids instead of rectangles. So the same idea, but we're going to add rectangles instead of trapezoids. Okay, example 1. Approximate from 0 to 10 by adding the areas of the 5 trapezoids shown. Notice these trapezoids all have a different width, so we can't use a formula when they all have a different width. So each trapezoid is different. If you really look carefully, the first shape is actually a triangle. You can think of a triangle as a special trapezoid, or think of a triangle as a trapezoid that only has one base, where a base is 1, you have one base and the other base is 0. It uses the same formula, half the base times the height. So, area number 1 is 1/2. The base, the height of the first one is 0. The height of the second goes up to 4. And the width is 2. Do it again. 1/2. The heights, add them up. The first height goes up to 4. The next height goes up to 3. And then the width of it goes from 2 to 5. So 2 to 5 is actually a width of, not 5, but a width of 3. So from 2 to 5 is a width of 3. Keep setting it up. We're not going to simplify it at the end. The next trapezoid, 1/2, the bases are the heights. So it goes up to 3. It goes up to 2. And the width of that is 1. Keep going. The height goes up to 2. The height goes up to 2. And the width, 6 to 8, is 2. Last one. The heights goes up to 2, goes all the way up to 5, and then the width of it, 8 to 10, the width is 2, and you've approximated using trapezoids. Note the area formula for a trapezoid also works for a triangle when one of the bases or heights is 0. So there you go. If you forget the formula for a trapezoid, you can always draw your areas as rectangles and triangles and not even use trapezoids. How sad would that be? Okay, example number 2. Use 4 trapezoids of equal width. That's going to make the formula easier to find an approximation for the area under the curve for y equals x squared, bounded below by the x-axis, and the left by x equals 0, and on the right by x equals 2. So first I'm going to draw the parabola, y equals x squared. 0, 0, 1, 1, and 2, 4. I'm going to connect and draw it. There's my half my parabola. It's bounded by x equals 0 and x equals 2 in the y-axis. So I'm finding the area trapped between the parabola and the x-axis using trapezoids. So they are of an equal width. We know that this formula, and I'm going to put the width in front, we're going to use for each one. That formula, I want you to notice that 1/2 and the width belongs to every trapezoid. We can actually factor it out in front. So if I set this up, the width for each one, and it says 4 trapezoids. So the upper bound is 2, the lower bound is 0, and we want 4 trapezoids. So what would be the width for each one? 2 take away 0 divided by 4, we're going to reduce it down. It's 1/2. So the formula is 1/2. The width for everyone is 1/2. And now we're going to go trapezoid at a time. All right, I want you to notice this. The height of the first one is 0. The height of the second one, we would plug in 1/2, because it's half there. And if we go 1/2 squared, that height is 1/4. That's one of them, right? 0 and 1/4. It's like right here. That trapezoid right in there. It's actually a triangle. If we do it again, what I want you to notice is that it shares that height. The trapezoids that are beside each other. So the next one's going to be 1/4, and then it's going to be 1. The next one's going to be 1, and then halfway up. So that's 3 over 2, and if you square it, it's 9 over 4. And again, it's 9 over 4 again, and then last one's 2. What I want you to notice is that the 1/4, the 1, and the 9 over 4, they repeat. So what we're going to learn for the formula is this. The first height you write down, but every height after that, we're going to double them, and double them, and double them. And then the last one we leave alone. So the middle heights we actually double because they're shared by both trapezoids. This is going to create a formula that we're going to use in the next one. So that's what the area is approximately. Let's turn the page. I'm going to use the other packet so that my blue marker didn't bleed through. All right, here's the formula I'm talking about. So the formula is 1/2. That width represents the height of it in terms of a rectangle, a trapezoid that's reorientated. It's now the width. And these heights, the first one and the last one aren't shared, but all the ones in the middle are shared by both trapezoids. So as I'm adding across, I'm actually going to add it twice every time. So now we have a formula that the middle heights we're going to double. So let's practice using the formula. First thing, use the trapezoid rule. And we have a table of values here. So if I look at the trapezoids, I want you to notice that they're of an equal width. So the formula is 1/2. And what's the width of each trapezoid? 10 to 20, 20 to 30, 30 to 40, 40 to 50. The width is 10. Now, the first height for 10, look off the chart. It's 1.8. I only use it once. The next ones I'm going to double because they're shared by two trapezoids. So at 20, the answer is 2, and it's doubled because it's shared by the left trapezoid and the one right beside it. At 30, it's shared. And remember, at 30 is 2.5. That's why I'm doubling it. At 40, it's shared, right, by both trapezoids. So at 40, look off the chart, it's 3.5, and then the last one is not shared, so you don't double it. So at 50, it's 2.2, and that's it. That's the setup using the trapezoidal rule. Oh, is there anything else? No, that's it. Now is your time to practice. Practice using that formula so you're comfortable with it. And unfortunately, I'm going to see you on Friday and not on Wednesday. All right, all the best.